All right, we're gonna go over the AP Classroom assignment. And it was pretty gnarly in a couple of places, so we're gonna do our best to go over it. So I'm gonna start, and you hopefully have the problems in front of you, and you're splitting a screen or whatever as we're getting used to this craziness. I'm gonna like this. Okay, so number one, gasoline storage tank filled with a pipeline from a refinery. At the same time, gasoline flows from the tank into trucks that will make deliveries to gas stations. The amount of gasoline in the storage tank is G, it's measured in thousands. That gets on my nerves. Just remember what that means is like 22 really means 22,000. On an interval from 0 to 10. Values of G, certain ones are given in the selected table. It's known the second derivative is bigger than 0 when T is between 5 and 10. Part A, use the data in the table to estimate the rate of change of the amount of gasoline in the storage tank at time equals 3 hours. So this is similar to that one we did in class. Estimate what the rate of change is of G when T is 3. So obviously I can't find out what the rate of change is at 3. I don't even really, even if they gave me the value of 3, I still wouldn't be able to figure it out because the rate of change is a derivative and I just have some random points. So I'm going to use the two numbers closest to 3, surrounding 3 or whatever, flanking 3 on either side, and find the slope between them. So I'm going to find the slope between the point 1, 18.5 and 5, 19.5. So G of 5 minus G of 1 over 5 minus 1, blah, 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 and I get 1/4. And this is approximately the derivative of G at 3, so I use the approximate symbol. And just so they asked for us to indicate our units of measure. When it says indicate units of measure, if you don't, you won't get that last point for that part. So it's not 1/4 gallons per hour, but this was measured in thousands. So it was 22,000, 18.5 thousand. So I just wrote 1/4 thousand gallons per hour or 250 gallons per hour. Either one of those would be totally fine. Okay, part B. For T between 0 and 10, is there a time at which G of T is increasing at a rate of 0.2 thousand gallons per hour? So they want to know, is there a time that the G of T is increasing at a rate of 0.2 thousand gallons per hour? So they want me to find out, they're indicating that they want me to use mean value theorem. They want me to see, is the slope between those two endpoints, between 10 and 0, what is that slope? And if that slope turns out to be 0.2, then yes. So I found the slope between 0 and 10, and I got 2/10, which is the same thing as 0.2, so yes, the mean value theorem does guarantee that there is a value between 0 and 10 such that the slope is 0.2. I probably also should have said somewhere that G is continuous and differentiable. So I know that because it tells me in the problem. It says G, the twice differentiable function G. That just means you can take two derivatives of it without a problem. So I do know that G is continuous and differentiable. Okay, part C, a linear approximation really kind of means just find the tangent line. So I'm gonna find the tangent line at T equals 5. So at T equals 5, I know my point is 5, 19.5 because it gives it to me in the original chart. It also tells me that the derivative of G at 5 is 0.5. So now I know the slope and I know a point and I can find the tangent line. So I find the tangent line, y minus y equals slope times x minus x. I get my tangent line. And now it wants me to use that to approximate the value of G of 7. Again, I don't have G of 7 in my chart, so I'm going to use the tangent line. 0.5 times 7 plus 17.5, and I get 21,000 gallons. Now they want to know, is this an over or underestimate? Well, this is what we were talking about when I was in class last week, that if I have a function and I want to know is G of, let's say, I'm saying G of 7 is approximately 21, and my function is, I want to know basically, is my tangent line over or under my function? Well, since they tell me that the second derivative of G is always positive, that means G is always concave up. So I will always be either concave up like this, or even concave up like this. It doesn't really matter. What matters is when something's concave up, the tangent line is underneath it. Whether I'm concave up and increasing or concave up and decreasing, the tangent line is below it. So the tangent line value will always be a little less than the actual value in this case. So using this tangent line as an underestimate, because the second derivative is bigger than 0, therefore g is concave up, and the tangent line is underneath g of x. All right, part D. Part D now gives us a totally new function, R of t. R of t is the rate at which gas flows out of the tank, and they want us to find the absolute max of that rate. So to find an absolute max, I take the derivative of R, I set the derivative equal to 0, and find the critical values. In this case, there are 2, positive and negative 2. But my interval goes from 0 to 10, so I don't have to worry about the negative answer. And now I'm going to test in a chart the critical value and the endpoints. I'm plugging these numbers into the original, into R, to get the y values. I get all 3 y values. This one gives me my biggest y value. So this is my biggest y value. That means this is where my absolute max happens at time t equals 2. Okay, number 2. I know this takes a lot of time. Number 2 I love a multiple choice question, right? Especially after an open-ended. Okay, find the absolute max on the closed interval 1 to 5 halves. So I have to take a derivative, set a derivative equal to 0, solve. I don't have to worry about x equaling 0 because it's out of my interval. So now I have to test my critical value, and I have to test my endpoints, put them back into f, look at my y values. The smallest y value is where the absolute min happens. So the absolute min happens at x equals 1, and the absolute min itself is 2. Beautiful. Nice, simple problem. Oops. Number 3, they give us this big chart. And they want to know, oh, by the way, I don't know about you, but my question looked weird. It says for blah, 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 when does a of t equal 0? I guess this meant to say for, I don't know, this function, whatever. For this function, when does the acceleration equal 0? Justify your answer. Oh, maybe that's, actually, when I went and looked it up online, it didn't actually, it was, yeah, it was like, it said some, shoot, now I have my computer closed with that. But I thought it said something like, can we guarantee that the acceleration will be 0? And I said yes, because from 0, oh yeah. Yeah, my question got like cut off, it was weird. Okay, I had to go check it again online. Anyway, it said like, can we guarantee that there is a value such that the acceleration will be 0? Well, so do you remember that when we have our original function, we usually call that s of t, or you guys call it x of t, that's the original position function. The derivative of that is velocity, and then the derivative of velocity is acceleration. Oops. So if they want to know what, if they want to know, is there a place where the acceleration is 0, which is what that's asking, then yes, there is definitely a place where the acceleration is 0 on the interval 0 to 25, because the y values are the same at the endpoints of the intervals. So Rolle's theorem must apply and the derivative must be 0 somewhere. That's all that that's saying. Sorry, it's me moving in my chair. Okay, number 4. Number 4 was just really algebra heavy. So, you know, I almost hate these questions because they're telling you the answer. Given that the second derivative, oh wait, so we have a blah, 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 blah. F of 0 is 2, f prime is -3, double prime of 0 is 0. This is g prime. show that G double prime is this. So they want you to go take the derivative and show your work. So this was my original, and I used the product rule. We have the first term times the derivative of the second, plus the second whole term times the derivative of the first. So think about this as two terms added. I got a big thing here, and I've got a big thing here. I took e to the negative 2x out of both and brought it to the front. So I was left with 3f prime of x plus 2f double prime of x. And then this negative 2 has to get distributed to both of these things. So I have a negative 6f of x and a negative or minus 4f prime of x. So again, that algebra is really gnarly, but I took an e to the negative 2x out of each term to the front, and everything that's left over I wrote down here. This is straightforward, but this negative 2 had to get distributed to both of those terms. Then I added up my like terms. I had a 3f prime and a negative 4f prime, gave me a negative f prime. I had a 6f or negative 6f of x and a 2f double prime of x. So my answer matched theirs. The question then was, does G have a local max at x equals 0? Well, this is an example of when that second derivative test is really useful, because to take the second derivative and plug in values smaller than 0 and bigger than 0 would be impossible. Because the way, what they're only telling me, if this is G double prime of x, I would have to be able to plug in like negative 1 and 1 into this, but I wouldn't be able to because they don't tell me what f of 1 is and f of negative 1 and all that stuff. So I can't use my normal make a number line and test on either side. It's not going to work. So does G have a max at 0? Well, first of all, I want to make sure the first derivative of G at 0 is 0. So I'm going to double check, take my first derivative and plug in 0. So I plugged in 0, I used those original values that they gave me, and yes, I got 0 for the first derivative. Now look at the second derivative and plug in 0. When I do the same thing, I get a negative number. I don't care that it's negative 9, I just care that it's negative. So G must have a relative max at x equals 0 because the derivative is 0. So that means I have either a min, a max, or potentially a point of inflection. But the second derivative is negative, so therefore the graph is concave down. So it looks something like choice number 2, so I have to have a max. It's a great problem. Go through that again if that, felt kind of iffy, because it's a really, really good problem. Okay, number 5, we have this picture. And first they wanted us to fill out this chart. So this is F. They're telling us F is positive everywhere. Makes sense, okay? Positive means above the x-axis. So my graph of F is positive everywhere, above the x-axis. My derivative from -5 to -2. So the derivative of F is the slope of the tangent line. Well, F is increasing, so my tangent line will be have a positive slope. F is decreasing, so my tangent lines will have negative slopes. F is increasing, so my tangent lines will have positive slopes. And decreasing, my tangent lines will have negative slopes, or my derivatives will be negative. Second derivative is talking about concavity. Well, this is concave down, so my second derivative is negative. Concave down, so my second derivative is negative. And now I don't have concavity, these are linear. So if these sections are linear, that means their first derivative of them is a constant. That means the second derivative of these parts is going to be 0. Okay, part B, do we violate the mean value theorem when we say that between -1 and 3, there is no place such that the slope between the 2 points equals the derivative at some point? So they're saying between -1 and 3, here's the line that connects them, there is no spot on that interval such that the tangent line has the same slope as this line. Mean value theorem says we have to. It says between 2 endpoints, whatever the slope is between those 2 endpoints, somewhere along the way, our derivative has to be the same as this. Or the slope of our tangent line has to be the same as this, and it's not. Why not, you ask? because the function is not differentiable here. Because of this corner, it messes the whole thing up. If this corner wasn't like that, so if instead my graph came down and then somehow scooped back up, well then there would have been a place where the slope matched the slope of the tangent, the slope of the function matched the slope of this. Maybe right here, or here. My tangent line would have the same slope as that secant line. But once I give a sharp turn like that, I don't have a guarantee. Doesn't mean it can happen, but it would be a fluke. The mean value theorem does not guarantee it. Okay, so I wrote this does not violate the mean value theorem because f is not differentiable at 0. Okay, now we really have to start like thinking a lot. Part C says find the value of x at which g has a point of inflection. Okay, sorry. My thing is starting to fall. Okay, g has a, okay, so I always try to go back to what I know. G has a point of inflection when the second derivative of g is 0 or undefined and changes sign. Okay, well, how do we look at g's double prime? How do we look at the second derivative of g? Well, they tell us g prime is f, so therefore g double prime is f prime. So we're really asking not when does g prime change sign, but when does, or I'm sorry, not when does g double prime change sign, but when does f prime change sign? Because they're the same thing. So go up and look at my table. When does f prime change sign? Positive to negative here, negative to positive here, positive to negative here. So all three of these spots, at -2, at 0, and at 3. The first derivative of f changes sign, so therefore so does the second derivative of g. So all three of those points. Okay, part D, where's an absolute max? So again, go back to what we know. Absolute maxes happen when the derivative of g is 0 and changes from positive to negative, because we do need to make sure we have a max, or at least that's something to think about. Or it happens at the endpoints. So first, let's see, when is the derivative of g ever 0? Well, the first derivative of g equals f of x. Where does it equal 0? Well, this is f of x. This equals 0 only here and here, so only at the endpoints. So they're the endpoints anyway. So really all I have to do is check the endpoints. Usually I would make a chart and I would test the endpoints 5 and -5. But this time, it's not so easy to figure out what g is, g of 5, g of -5. Because I can't even find out what the slope is here. I guess I can here. But one thing I thought is, they tell me g is increasing on the entire interval. So where must the max happen? Well, if g is increasing the whole time, is the max going to be at the leftmost endpoint or the rightmost endpoint? Well, it's going to be at the rightmost endpoint at x equals 5. Okay, that's a lot. I don't know if it's any easier to understand in person. I don't really think so. I keep going back and thinking like, you know, in this way that we're learning, is this a mess? And yeah, sure, it's a mess, but it's not a mess necessarily because of the videos. It's a mess because it's really hard. So, you know, one thing I like about a video is you can go back and you can check and blah, blah, blah. So that's it for today. Have a good day. I'll see you later.